Hello, my friends. This is a flight that has made quite a splash. This was a flight organized by the Moroccan national airline Royal Air Maroc in 2016, and it almost ended extremely badly. To be honest with you, you look at the hundreds of videos on this channel. We don't know of a single plane that came back from so far. It was a situation from which normally no one comes out well. As they say in Morocco, it means there was probably a divine hand that protected the 155 people who were on that plane that day. But the pilots also had a hand in it who took absolutely extraordinary actions and saved that plane at the last second. Now, if you were on that flight, what I advise you to do is to contact the local authorities and request a new birth certificate with the date December 30th, 2017. To me, that's where you were born, a new life starting for you. Let's take a look at what happened that day. So, if we take the year 2016, starting from mid-2016, basically from the summer, we have this Boeing 737-800 that starts to have some issues. So the issues are of this nature. We have the ADIRU, I'll explain what that is on the left, plus the right radio altimeter, which have intermittent problems. So, roughly speaking, to explain the setup a bit, on the 737-800, we have two controllers. We have two controllers, FCC 1 and 2, or right and left, or A and B, whichever you prefer. And then they're paired with two autopilots. Autopilot A, autopilot B. These are two-axis autopilots. That means they control the plane when it rolls, or when it pitches, or when it pitches up. They are extremely simple, extremely efficient, and they generally work separately. So we either have autopilot 1 working, or A, or autopilot 2. Today we'll focus on a phase where both work simultaneously. We'll discuss it shortly. Après, next what we have is two boxes that we call adires. So adires are boxes typically made by Thales, and they provide two things. Actually, it's two systems inside the same box. We have an R part, which means it's a part that will provide, for example, altitude, indicated airspeed, and the Mach number. We're not interested in that one today because it has always worked without any problems. The other part of the box contains gyroscopes, and that's where we have the inertial side. So the gyroscopes we have here, and generally in all modern aircraft, are like this. They're no longer those gyroscopes that spin at high speed, those bronze wheels that spin very fast. Today we have what we call lasers. It's simply lasers in a box. And then they bounce around mirrors. And that also allows us to do exactly the same job. It was actually invented by a Frenchman a little over a century ago. He was the one who discovered this phenomenon that's used in these gyroscopes. If you want, I suggest you subscribe to the YouTube channel parkourtech.com. You just enter the domain name parkourtech.com and you'll get right to it because it's a channel where I explain a lot of the theory. And then in the future, there will be a video about this system. Anyway, what you need to know today is that we had intermittent problems with the left ADIRU, the A unit. And when it's intermittent problems, it's not easy to troubleshoot. For all complex systems, we prefer them to have clear failures. But as for a failure that's there, that's seen by the pilots, for example, just to tell you, in December, this aircraft was making a Category 3 approach. That means a Category 3 ILS approach. That means in zero visibility with the intent to land automatically. It reaches about 10 meters above ground. Both autopilots disengage. You see, it's still very serious. Why? Once again, it was that ADIRU that was acting up. So what's happening is that, to be fair to the technicians and the airline, they've made a lot of effort. They really didn't hold back. They replaced a radio altimeter, they replaced the antenna, they replaced an FCC. They replaced a lot of things, but unfortunately, since the malfunction is intermittent, it's very hard to pinpoint because you replace something, you run tests and everything, and you feel like it's going to work. The aircraft can even do 2 or 3 flights and it's fine. Then one day, bam, it starts again. Okay. So as I was saying, during this flight that takes off a little before 8 in the morning, suddenly the message appears. Received envelope? That means an error on the right side, or rather on the left side. So this one slowly starts causing problems again. So here, what happened was a drift problem. Because what happens, you see, since we have a box, well, it has tests inside. And how does it know if there's an issue? Well, it has a certain number of algorithms that are constantly running inside, checking whether the values produced by this Adiru are reasonable, are plausible. It failed the plausibility test that day. In fact, if you want, the logic was as follows. One of the logic checks that was triggered was this. An aircraft that goes over 200 knots, and then we take the heading, the magnetic heading, that's one value, but where does the 200 knots come from? The 200 knots is from the R part, not the inertial I part. So we take the 200 knots from the R part, we take the magnetic heading, that also comes from outside the Adiru, you see information from outside. And then what we ask from the Adiru is the track, because gyroscopically it can calculate the track. If there's over 60 degrees between the heading and track at speeds above 200 knots, there's a problem. You see, so that's one of the plausibility tests that it failed. That is to say, clearly the heading was correct, the speed was correct, but the track calculated by the Adiru was wrong. The inertial part was wrong. So it calculates the track, it gives him that, he says, my track is greater than the delta between my track and the heading, so the crab angle is greater than 60 degrees, that's not possible. And so there's a problem. It outputs the IR-fault message. So the IR-fault message comes out, but then it will disappear. So once again, you see it's a message, an intermittent message. The message appears, and then bam, well, there's no more message. We keep flying. So what happened is that Orly Airport that day, well, a good part of France, actually, since it's winter, was covered in fog. It's early in the morning, and the country is still in the fog. So what we had at Orly Airport, so we're arriving at Orly, and what we have is that Orly runway 06. What we have is that we have conditions of type 43, so it's ILS 43, okay? Which means that this ILS 43 issue makes it so that on that day only planes capable of landing automatically, because it's an automatic landing, well, can come. So what happens is that normally when we operate, in normal operation, for example, during cruise, if autopilot A is engaged, it mainly works with its own FCC. There's barely any exchange, only a few elements are exchanged, and even those are rare. However, when we do a Category 3 approach ILS 43, well, by design, by certification, both autopilots are engaged. In cruise, it won't work. In cruise, you can't engage both, but if the approach mode is engaged, it allows you to engage both autopilots. It's mandatory for this kind of approach. So once both autopilots are engaged during the approach, so we have this one and that one engaged, we have more communication between the left and right FCCs. So we have a stronger comparison of information between this one and that one. So indirectly between the DRE-A and the DRE-B. You see, so there's this kind of comparison. We're moving from a system that's normally high fidelity to a system that's very high fidelity simply because we're allowing the autopilots to land the plane in a situation where there's no visibility. So we need maximum reliability to make sure that a single error or any kind of mistake doesn't happen in the control chain, and bam, we end up causing damage. So what's happening is that our aircraft is starting to approach runway 06. At some point, we reach an altitude of around 2,500 feet, where the radio altimeter, both radio altimeters, should start giving readings. Because the radio altimeter is not a barometric altimeter, it's an altimeter that sends waves toward the ground. And then see how long they take to go and come back and measure the height above the ground directly. It's a direct measurement of height above the ground. That's exactly what allows you to land. That's what allows the aircraft to know exactly how many meters it is from the runway and lets the wheels gently touch down on the runway. So it's absolutely necessary. So at a certain point during the approach, here's what happens. The FCC here, FCC-A, receives information from radio altimeter A, so that's good, but FCC-B here doesn't receive anything from its radio altimeter. So what happens? There's something is missing. In comparison, we look, we analyze, we say, there's something missing, so what we're going to do is discontinue this approach. Because this approach requires both radio altimeters, for redundancy reasons, it requires both radio altimeters to be working. What's going to happen? Well, both autopilots are going to disconnect. Click, click, it's over. Both will disengage. So the pilots realize they won't be able to land at Orly because you need to be in category 3. So you need both autopilots, but now they can't engage both. So what do they decide to do? The only thing to do is to go land somewhere else. So they will go to their alternate airport, which that day was Lyon. So they are going to head to Lyon. And so in Lyon, the conditions are slightly better, but not much better. Here in Lyon, the ceiling is about 500 feet above ground. 500 feet. So the sky is completely overcast at about 500 feet. So that gives us a category 1 ILS here. So category 1 is good. It's less restrictive than category 3. And here's the advantage. You can do this with just one pilot, with just one autopilot. So what we do is use just one autopilot. We descend, we go down, we break through the layer, we go below the layer. So we break out below the cloud layer. As soon as the pilot sees the runway, bam, he disconnects the autopilot and continues to land manually. In 4.1, it's not possible to land automatically. There's only one autopilot and it will refuse to land. It can't land, so you need both. So here, what's going to happen is that we're going to go with something much simpler. So what the pilots do is they're approaching runway 35R in Lyon, and they're going to use this autopilot, the left autopilot. So remember, that's the one that has a problem with its inertial system, an intermittent problem. So they're descending, they're on the center line, everything's going smoothly. And suddenly the aircraft, without warning, is going to make a turn, a pretty sharp turn, a 30-degree turn. So it's going to bank 30 degrees to the right. And then it's going to head off. It's going to take a heading that's 60 or 70 degrees off from the runway axis it was supposed to land on. So we're literally heading roughly on a 350 heading, runway 35. The wind was light. And what happens is that suddenly it turns right and heads toward heading 60. So it doesn't make any sense, but the autopilot will follow. And why? Because since that one is malfunctioning, it's sending bad track data, and the FCC takes that bad track data, passes it to the autopilot, and the autopilot follows it. Since we only have one autopilot connected, we don't have any comparison here. And there you see why for the 43 there's a requirement for 2 autopilots. Because if we're only using one, there's no cross-check between the 2 FCCs. So a single error here on this Adaru, well, it's going to corrupt this autopilot, which will start doing all kinds of random things. So it just behaves erratically. It's going to start going off like that. There you go. The human pilots realize the problem. They take back control of the aircraft, but put yourself in their shoes. At that point, they start to lose a bit of confidence. At that point, their faith in the integrity of their aircraft is greatly shaken. They are forced to go around. So here, I'm counting. So here, we had a go around in Paris. Now we have a second one in Lyon. And so they go around. They make a turn. There you go. They're asking themselves questions. What's going on? All of that. And they decide to come back to land. So this time, since the left autopilot, that one couldn't help them. And now it's kind of acting up. They say to themselves, we'll use autopilot B. Okay, so they try another approach, but this time with autopilot B, the right one. Now look at what happens. While they're figuring it out, approaching, they arrive at a moment when this one is supposed to indicate a height. Well, it doesn't indicate anything. Since it starts acting up on the radio altimeter because it also had an intermittent problem, well, the FCC gets bad information here. It tells the autopilot disconnect. And so the autopilot disconnects. I'll keep it simple for you. What also goes away are the bars, the magenta bars of the flight director. The flight director is a way for the FCC to communicate with the autopilot. It's 2 bars, 1 vertical, 1 horizontal, and it's a way for the FCC to tell the human pilot, if I were you and wanted to follow this trajectory, here's what I would do. So it helps a lot with manual flying. You find this on Boeing, Airbus, and other aircraft. And when there's manual flying, ideally what we do is follow the bars. We try to put the little airplane on the bars. Well, the magenta bars make things much simpler. When there are no more magenta bars, it becomes much more complicated. So there's also something else that doesn't work. It's the system. And that, strictly speaking, at the moment, taken in isolation, isn't a big problem, but it further undermines trust in the aircraft, the auto brake system. So normally, sometime before, the pilots turn the selector to choose a deceleration setting. 1, 2, 3, what kind of braking do they want? A higher number means sharper braking. And actually, this system is always powered from the left DRU. Why? Because when it is activated, it communicates with the left DRU to get the acceleration and to get the ground speed. It needs these two pieces of information to know how to properly manage its braking. Well, when it is engaged, it receives an error from the left DRU. And what does it do? It sends an error, it can't function. So that's another little detail that will worry the pilots. On top of that, they're worried because of that since they're attempting their third approach. And now the fuel, they have about 2 tons. Right now they have 2 tons of fuel. So it's slowly starting to get tense. So we have IMC conditions, instrument conditions, fog, very low clouds, and a plane that's pretty much doing whatever. From their perspective, they don't have time to analyze everything I'm telling you, since they're in the cockpit and things are happening quickly. So what they see are systems constantly failing, giving random information, autopilots, whether left or right, doing whatever, you see. So now it's starting to get serious. So as I was saying, during this third approach, autopilot B fails. The flight director system also fails. And what are they going to do? They decide to continue to keep going manually using raw data, as we say, so just with the basic pure data without any assistance through the clouds. So what will happen is that they will gradually get alerts. There will be alerts in the plane, alerts on the ground. In the plane, there will be GPWS alerts. It's a danger detection system for contact with the ground. So it's going to start yelling at first about the descent path. So it will say, glide slope. Glide slope will notice they are below the descent path. So that's already one thing. Then it realizes that the ground is approaching faster and faster. So it starts escalating in terms of alert. So the pilots are trying to find that damn runway in the cloud with the GPWS yelling at them, telling them, warning, you're about to crash. In the control tower, there's something called the HEMSO. The HEMSO is a radar system that analyzes the planes and their relationship with the terrain. And when it sees that a plane is in a danger zone, it will alert the air traffic controller, who must inform the pilots. Except that for several seconds the HEMSO is signaling, but the control tower in Lyon isn't in contact with Royal Air Maroc. Why? Because it changed frequency. It was on the approach frequency. It was supposed to switch to the tower frequency, except it was on neither one nor the other yet. And so now the situation is seriously getting out of hand. At one point, the plane suddenly appears below the cloud layer. So there are 2 parallel runways like this. It appears here about 1 kilometer between the two, and it's at 180 feet above the ground. So here it's about 60 meters above the ground, roughly 1 kilometer from the runway, which is extremely, extremely low. He should usually cross the threshold at that altitude. If there had been a tall antenna, if there had been a big building, anything like that, this was a case where he could have hit it. So he comes out. What do the pilots do? Since they're very worried about the fuel, they said they have 2 tons, plus they're worried about the whole aircraft not working the way they want. And so they don't want to go back into that layer and maybe have even more problems and not even know how to come back. And they don't have enough fuel left to try to go to another airport. So what do? They're going to do this. They're going to make a sharp turn to the right and another to the left to land. So during this turn, at one point, they measure more than 1,000 feet per minute of descent rate on the vertical speed indicator, while they're at 80 feet above the ground. That means that at one point, the aircraft is weaving at very low altitude, trying to line up with the runway. So it's going to make runway 35 right. It's going to land several hundred meters after the touchdown zone. Bam, it lands. The pilots brake, exit the runway slowly, and then that's it. The problem here is that they were saved, as you can see at the last minute, by two intermittent failures, one on each side. Now, where there's a big problem is what happens next. What happens next is that they call their airline. There's a mechanic who will troubleshoot over the phone, and then what happens is that the plane takes off again as it is. So the plane takes off again, and it goes to Orly. The weather had improved a little, so we were no longer in a situation like in 43, but the aircraft went to Orly. Honestly, I'm telling you this as a passenger, regardless of the airline. If I see scenes like that, it means approaching an airport, going around, then going around again to another one. And then a rough landing with slaloming just above the ground and all that. I can guarantee you when I get off the plane, I take my things and I'm out. I'll take the high-speed train. I'm not getting back on the plane. Anyway, people today have a lot of trust in the system. So what happened was the plane arrived at Orly. It landed. After Orly, it takes off for Marrakech. It arrives in Marrakech. There's an autopilot problem during landing. Fortunately, the weather was good there. So the pilots were able to turn off the autopilot and continue the landing manually. It will fly again at the beginning of January. Until then, there is no investigation or anything. And suddenly it was the end of the year. People were on vacation, holidays and all that. Quite simply, we arrive on January 23rd. Someone from the DGAC hears from the Lyon ATC that there was a Moroccan Boeing 737 Oscar Juliet that was very close to crashing. And then we call the BEA, which is the Accident Investigation Bureau, and that's where the investigation begins, and that's when the investigation will involve the Moroccan authorities, the French authorities, and all that. What was lost in all this is the CVR. That means the voice recording inside the plane because the aircraft remains in service. When an incident occurs, promptly inform authorities so all the evidence is collected while it's still fresh. But since then, there have been quite a few changes. And the investigation was carried out and it was considered an extremely serious incident by all the parties involved. Moroccan, French, but also TLSB and Boeing. Actually, if you want, it's just a coincidence, an unfortunate combination of circumstances also related to the design of the aircraft. You should know that the Boeing 737 has a design from the 1960s. And then later on, we released quite a few versions by adding systems on top of each other to make it a modern aircraft. But it will never be as modern an aircraft as the Airbus A320, for example, because the Airbus A320 was built from day one to be a plane with a lot of processors, computers, automation, and all that. Whereas with the 737, practically everything was added afterwards, and each time we try to connect things thinking, why not do this or that? For example, among the assumptions pointed out by the BA is the assumption about the time it takes to detect an error and then the time it takes to react to it. You should know that at the time of the Lion Air and Ethiopian Air accidents, you remember the story of the MAX, I covered both accidents on this channel, there was a joint commission between the NTSB and NASA in the United States. They started conducting tests to find out how long it takes pilots to identify a problem and react. You should know that Boeing, in its aircraft design logic, accounts for a lot of errors. Based on the assumption that they'll recognize them within 1 second, that means that pilots will, for example, during the approach, in 1 second, they will realize that there is a problem and will start to intervene after 3 seconds. These are the assumptions that are made when a system is built, when it is certified. But when this working group started asking questions, well, no one was able to explain where these numbers of 1 and 3 seconds came from. And very often that's how it is in aviation regulations. We have numbers that were written sometimes in the 1940s or 1960s by someone who isn't even with us anymore just because a number was needed. Maybe it was just an estimate back then. And later on we use them again. One circular after another, one regulation after another, and it's still being used today. And then when we start looking into it, no one is able to explain. And it's necessary, and that's actually one of the BEA's recommendations in this accident or this serious incident, that we need to conduct more realistic studies. That means bringing groups of pilots, putting them in simulators, running tests in different scenarios to really see how long it takes them to detect a problem and to react. And the truth is, it takes them much, much longer than 1 second or 3 seconds. That's it. But in any case, congratulations to these pilots who managed to there's nothing more to say. They managed to save their own lives and those of their passengers, as well as prevent a lot of material damage. And then I'll see you in the next video. And remember to subscribe to the Parcours Tech channel, because there you'll find more detailed theories, fewer accidents, maybe no accidents at all, but more detailed theories. See you very soon.